Hello, ladies and gentlemen, and welcome to this three-part series in Pivot 2023 titled Uncharted Territory, Demonstrating Novel Geothermal Solutions. My name is Mattie with Project InnerSpace, and I have the pleasure of moderating this session for you all today. The session is composed of three separate presentations, given each by the CEOs of Canopus Drilling Solutions, Q-Heat, and Eden Geothermal. Each will be a 20-minute presentation, followed by question and answer from what you and the audience may want to ask. And now let's begin with Mr. Jan Jette Blangé of Canopus Drilling Solutions, coming to you from the Netherlands. Jan.
Hi, everybody, and thanks a lot, Taylor, for the introduction and setting this up. And of course, also Project InnerSpace for organizing the whole Pivot the event. It's great to be here. So it's great to present Canopus to you all. Canopus has been founded in 2019, so really a fresh company. Within those 4 years, we managed to get from really nothing to a series of patents and some hardware, and even a pilot we executed just 2 months ago. And I will try to give you an impression of that during this presentation. Yes, so let's go to the next slide. First of all, the name, of course, that talks better. Canopus is a giant, supergiant star. And the fun is that the sun and other smaller stars are not heavy enough to produce steel. Steel is the core of the earth, I should say iron, and that's where the geothermal energy is coming from. So everything is linked together in this way. Anyhow, geothermal is, of course, a sleeping energy giant, and what we try to establish with Canopus is that we want to try to wake that sleeping giant by the development of the directional steel shot drilling. Then, what is directional steel shot drilling? And I need to use a different device. Steel shot drilling is using, obviously, steel particles. These are spherical and less than 1 millimeter in diameter. They have to be injected in the drilling mud. So right after the high pressure pump, that's a standard pump on a rig up to 5,000 psi. Then the steel particles are injected in the pressurized mud stream, circulated through the drill string to the bit. And of course, that is a special bit because that is using not only PDC cutters, but it is also using the steel shot, the jets laden with steel shot to erode away the target formation. So that way, it is really a hybrid hole-making action coming from this special, say, modified PDC bit. Later on, you will see a picture of it. Right before the particles reach the steering sub, they travel through a steering sub. And that steering sub requires a little bit more background, which I will go into after the next slide. The next slide concerns the injection system, just to give you an impression of the inside of just a 20-foot sea container. It's a standard container. On the inside, there are 2 pressure vessels, which contain each steel shot particles a load. And each container can inject those steel shot particles in the pressurized mud stream. By having 2 vessels, you can, of course, alternate the injection and that way get to a continuous injection. We need only relatively small particles, small vessels, because the concentration that we need is about 0.5% of volume, and that is much less than usually the concentration of cuttings, for instance, if you have a regional rate of penetration. That is very important for hole cleaning and for other operational things. So the steering sub, a bit more information on that as well, and that is a lot of the intellectual property of Canopus is in the steering method. The particles, the steel shot particles, are pumped through the drill string in a more or less continuous, with a continuous concentration. When the particles reach the steering sub, then they are converted from a continuous stream to a pulsed concentration. That doesn't take much energy, but it has a big effect on the erosive action of the bit. if you have these pulses and the jets in the bit are not symmetrical, that means that if the jets are aimed on one side of the hole bottom and then the particles arrive with a high concentration, you get more erosion on that side of the hole bottom than when you have rotated 180 degrees further, and then you are at a minimum of the particle concentration, and then you erode less. So it is really steering by controlling the concentration of the particles in the steering direction. The way we create these concentration pulses is by having a dual conduit internal construction in the steering sub. One conduit, which is the larger, the outer one, is just guiding the particles, but has a number of restrictions, so the particles are scattered. So whenever they enter that channel, then they are distributed in time, and you lose all the timing of the injection of these particles into the bigger channel. When the particles enter the smaller channel, then they pass through without any restriction, have a very well-defined travel time, and then when both channels are recombined in the end, you get pulses from the inner channel and you get just a continuous flow from the outer channel. The combination gives you, of course, a base concentration which is constant, and on top of that an oscillation which you can perfectly control by dumping the particles at the right time into that small channel. And that way you can get the pulsed concentrations. On the right hand side you see a borehole in limestone, hard limestone, Belgian limestone, and you can see that an S-curve has been drilled in that limestone. And if you look at what curvature you can establish with the steel shot drilling, it is much less than 10 meters radius. Of course, you can also reduce that steering action by controlling again the concentration variation in the bit. And then you can drill a larger radius, which is more consistent with, for instance, the stiffness of your drilling assembly, and perhaps later on also the stiffness of the casing that you want to place in the borehole. To the next slide. So just in short, the benefits of this hole making technology are that you can drill with a much lower weight on bit, but with a very high rate of penetration, and low weight on bit, and with that also the low torque on bit. You reduce the vibrations and also the bit wear of the bit. The directional control hardly consumes any power. So we had during the previous pilot, we had one battery and we could work with that for 4 days. It is accurate directional control, and because you have less vibrations, you can also better keep the direction constant as well. The whole system is a rotary steerable system, so you have the benefits of the smooth borehole and the continuous control while rotating. And because you're rotating, you have you have the friction factor perpendicular to the drilling direction, and with that, of course, better control of the weight on bit as well. The assembly can be maintained on the drill floor, which helps, of course, with the cost reduction and with the simplicity of the system. And the third point is a very important one. With the combination of the steel shot particles and the PDC bit, and especially the configuration that we have landed on, you have joint hole making action at the same radius of the on the hole bottom, and then you have both hole making methods enhance each other, and the specific energy of the combined action is much lower than the specific energy for only the PDC cutting or only the steel shot jetting. So, summarizing, directional steel shot drilling, DSSD, is great for fast drilling of long multilateral boreholes. But why is that so important for geothermal? Well, if you look at geothermal, there are, of course, several ways you can describe the market. We have looked at the depth for shallow geothermal, which is especially important for the heating and cooling of smaller facilities like musea or small neighborhoods. Therefore, we can, with this technology, relatively cheaply drill curved closed-loop borehole heat exchangers. And these closed-loop borehole heat exchangers, you can create them in such a way that all the legs, all the heat exchangers are departing from each other, are moving away from each other, which means that you have less crosstalk of the thermal behavior in the subsurface. And on top of that, you can start from a relatively small footprint, and especially in urban and populated areas, that is a very important benefit of the technology. So it is also, these are typically relatively small projects with short lead times. And that is, of course, perfect when you have a relatively novel technology to set up these type of operations for fast field hardening. And probably that is, we have already lined up a number of these operations for next year. Then we go to the deep geothermal operations, and then we are thinking about the greenhouse doublets that are very popular in the Netherlands. Then what a TNO study showed is that if you drill the type of multilateral structures, not exactly as in the schematic, but with several legs in both the producer and the injector, you get a much higher productivity than if you would have a single completion of 8.5 inch of 7 inch in an 8.5 inch hole in these type of reservoirs. Especially if the reservoir is not perfect and very open and needs to be stimulated a bit more with flow, then these multilaterals help a lot. And we have found that up to say transmissivity of 100, we have a very clear benefit of the multilateral structures that can be drilled with the DSSD. Of course, with these multilaterals, you also have a higher chance of finding good reservoirs. Especially important if you have if you want to produce through faults. Then the third one are the large closed loop structures. Of course, you have probably all seen these type of structures on various websites as well. It's a great vision, but to make this vision a reality, you have to drill a tremendous amount of a tremendous length of borehole at very large depth, and with that you have to be very fast in the drilling, and you need at the same time very good directional control. Otherwise, you cannot create these closed loops to be able to circulate your fluid and extract the heat with this closed system from the deep. Of course, it's great to have this hole-making technology. I think it is an extremely good candidate for it, but still we use electronics, and we will need to have what we call then cooling while drilling in one way or the other, or insulation or whatever, to have the electronics survive the potentially damaging high temperature of the formation getting into the steering sub. But then how did we get there? We did a lot of testing at the TNO Rijswijk Center for Sustainable Geoenergy. That used to be the lab of Shell. TNO took them over and made them accessible for the public, which was great. We did a lot of testing on downhole hole cleaning and on ECD impact. Extremely important, of course, because you need to be sure where the steel particles are, and you have to be sure that you can circulate them out of the well. We tested that. I'll come back to that on the next slide. And also in Rijswijk, we did a lot of testing to know exactly what happens downhole from the test in the lab. We tested in all rock types, so you can drill through granite, limestone, but also through permeable sandstones and also shale. And of course, the downhole conditions, especially hydraulic pressure, will have a big impact on the RRP, and therefore you should always, with a new hole-making technology, do these tests inside a pressure vessel where you can increase the downhole hydraulic pressure of the system. And on the left-hand side, you can see that the borehole quality is really great, which is great, also important for the directional control, of course. Now then, this is the one but last slide. This summarizes the results of a very recent field pilot we did with the directional steel shot drilling at VSH, that is Versuchsstelle Hagerbach in Switzerland. That was done in June. We only have recently been able to finalize all the results of the test. We had, first of all, safe operations, no damage. We drilled 2 horizontals with a hole size of 4 1/8 inch And we drilled we drilled at certain operating settings. And then when we switched on the steel shot, we had up to a factor 3 faster rate of penetration, again confirming that the steel shot and the PDC cutting are together working very well, and that you have a significant rate of penetration improvement while steering. And the steering is, of course, the first thing you have to be able to do with steering is to be able to drill a tangent, so unsteered, a straight borehole. We did that. We also made 3 turns in the range of 5 to 10 degrees per 30 meters, and that is consistent with the stiffness of the assembly as well. We had good hole cleaning for the settings that we expected. Normal flow rate, the pressure was up to 200 bar or 3000 psi. I mentioned already the battery life, and the steel shot concentration of 0.5 was good enough for all these nice features. So conclusion is that we are ready now to build the first 6-inch directional steering sub with steel shot drilling, and that's what we are going to test next year in a deep well. That pilot has been lined up already, and that is what is going to happen in the Netherlands then. And as I mentioned, we also have a number of shallow operations lined up as well. So we are getting there. We hope to go through the learning curve as quickly as possible. Then the final slide concerns the acknowledgement. Of course, we could not have done this at all as Canopus on its own. We have a great consortium. In fact, we had 2 consortia, one for the lab testing at TNO, and the other one was for the pilot in Switzerland, with a lot of overlap between all these parties. I'm very happy with their cooperation. It is the intellectual property is with Canopus, but of course the collaboration with all those parties that want to see this technology work for their own interest is great, and we had a great team together. So together we definitely want to wake the energy giant, just to get back to the first slide on the supergiant star. Thank you very much. I think I'm 2 minutes ahead of time. But,
yeah, and thank you so much. I really appreciate that. I always find this technology pretty fascinating, and I had an old colleague who referred to it as a type of technology called a Gatling gun when it comes to drilling. The first question, and there's a lot of questions coming through on the technology side, and we'll get to that in a second, but the broad question I want to ask you is, in the last panel, there was a term that was used that I enjoyed called death by pilots. And it's talking about the balance between technology, the business case, and the commercialization pathway. So to you, what is the timeline to full commercialization and scalability that you see for Canopus?
Yeah, I think that's it's the most important thing to me is how you do that. And concerning the timeline, if you take careful steps and not make them too big, if you make a step too big, then the reputation goes, and it's very hard to get back. If you make the steps too small, then people get impatient, of course. So the timing and the step size of the de-risking is extremely critical to get this done. We started with, say, the first patents in 2019. We had first, it took quite a while to get the funding for the first lab prototype done. And then in 2022, we had that prototype tested in TNO. And then it took about a year to get the first pilot prototype, which is a smaller size than the first commercial size that we want to do. But it makes that development cycle a bit faster. And the 6-inch first commercial size that we do will be ready for the first field testing next year in 2024. After that, you still need about 5,000, say, operating hours, or say the first 10 jobs will yield a lot of learning and what we call then the field hardening, to get really know the response of the technology to different settings. And we definitely don't want to go to the most challenging setting first, but build it up from shallow to deep. And that's a gradual transition, say, from piloting to the first applications. and that field hardening, and as also the pilot selection, I think it's very critical to make the development a success.
So you're saying what, maybe 3 to 5 years, you think, till full commercialization?
Yeah, so next year, I think we can start the commercialization for the shallow drilling, and then that means building another unit in the year thereafter, and perhaps grow faster if that proves itself. So that will be in 2 years' time. And for the deeper, I expect that next year we will have the first application. Then you have a longer lead time for those pilots, because that's deep drilling, and you have to have many more parties to get involved. So I guess that will take a bit longer than the curve for shallow drilling.
Yeah, that makes sense for sure. I guess before we move on to the technology questions that are coming through, on the commercialization side, what is the business case? I mean, why does this make sense over just using a traditional PDC bit, or how does it compare, and why should it be something that's looked at with interest rather than just what is currently being deployed within the oil and gas industry, and then also in the geothermal space?
Yeah, no, the fact that you can drill multilaterals, also sidetrack out of an open hole, and make much shorter turns than what you can do with conventional, much stiffer drilling assemblies that are based on rotary steerables or whatever. And that opens up really much more specific and optimized, say, reservoir sections than what you can drill with conventional systems. So we can turn around the corner, if that is required, a 90-degree turn within 20 or 30 meters. And if you optimize your drill string, you could even go shorter. But then, of course, you want at the same time to have the reach as well. And the reach for this system is because of it is a rotary steerable system, and you don't need much weight on bit. The reach, especially at a depth deeper than 1 kilometer, is at least another kilometer in horizontal direction in step out. So you can, from one well, you can sidetrack, you can drill in several directions, and you can create a much more, say, advanced network in the reservoir with a much lower drawdown than what you can ever produce with conventional purely mechanical drilling systems. And that boosts the productivity of these structures for the deep and the shallow. And we have these references now, can boost the productivity by a factor of 3. And that is, of course, if you get 3 times more heat production from your well, that means that you have to drill only 1 well instead of 3, which is a tremendous cost reduction, obviously. And the cost for drilling these boreholes, because of the simple BHA and the effective and the high rate of penetration, is max 20% higher than what you would do on top of a single well, which is pretty limited.
Yeah, I mean, that's significant cost savings. Absolutely. I guess so. As a segue then into the technology questions,
Yep.
Let me just ask the broad question here: is what are the remaining challenges that you have that you have to face on the technology side before you get to this point of what we call full commercialization?
Yeah, no, what we so we have looked at the hole making, we have looked at the hole cleaning, the complete integration of the system onto several platforms. We have had a look at that as well, and we know about the ECD and all the mechanics. So what we need to learn is how the directional control is over a longer distance. For that we need to make meters, and for that we need operational experience, and we will get tricks like the response and the delay time between. So there is a lot of bit mechanics, and there is always also a kind of a sidewalk tendency of a bit at certain weight on bit and at certain mechanical and probably also steel shot erosion settings. And we have to learn how that exactly behaves. And we have a feedback loop in the steering sub to correct it. But how that works out, how to optimize that, that is something that we will learn. And also the balance between the mechanical cutting, so that's just rate of penetration, the mechanical cutting of the PDC cutters themselves, and the erosive jet. We can tune at surface the total amount of steel shot that is circulated, and of course we can tune at surface also the weight on bit and RPM. These work together, and you have to optimize that, and we need more operational experience to sort that out.
Okay, so let me hone in on one of the points that you brought up, because there's a lot of questions asked about how what you are developing and demonstrating integrates into existing platforms. So there's questions on, does this work with RSS? How do the particles interfere with different measurement systems? What are the recovery rates? What are the communications? So I'm wondering if you could spend a couple minutes to go into how you guys have looked at the way this technology will strap onto existing tech that's deployed, and maybe answer some of the more technical questions on how it actually integrates into existing tech. Yeah,
so for instance, for directional drilling, you need an MWD, and then the idea was that the particles might interfere with the MWD, the directional sensors. We tested that as well during the pilot, and there was no deviation at all of the magnetometers in particular. So the azimuth reading was constant, whether we circulated the particles or not. So that's one of the things. The other thing, a question that we have had in the past as well, is whether the particles could get into connections and can damage the thread of drill pipe, for instance. During the pilot again, we had quite a lot of connections made and broken, and we did not have to stop or correct any of these joints in the operation. What you do need to do is when you have a break for the circulation because of a new connection, then you would like to time the steel shot circulated through the system in such a way that you have the bit more or less free of steel shot particles. That is not a prerequisite, so we have done also testing with just dumping a number of particles into the drill string and see what happens if the pumps break down, because that happens as well. Whether you can restart the system. You can restart the system, and that is primarily based on the ratio of the particle diameter and the nozzle diameter that you use, and the fact that they're spherical is very important to get these particles going again. So if you have edgy particles that you can put pressure together into a kind of a pancake, then you get a nasty blockage, and you should not have that. But with these spherical particles, that is working fine. Then the recovery rate. So we circulate these particles into the well. Then we separate all the solids, the cuttings, and the steel shot particles from the shaker. Then they flow over a magnetic drum separator, and that separation is better than 95%. We did not focus too much on that during the previous pilot, but we got the majority of the steel shot we got back, and you can during previous tests that I've done in the past with a previous employer, we have done also quite a lot of steel shot handling and could recover more than 98% during a full day of operation. So that is, and then you reuse the particles. They don't suffer from the impact. So you could imagine that the steel particles after impacting because of the jet onto the rock face, you might break a number of them. But the steel particles have a say an elastic limit, and you reach that elastic limit only at the moment you have say a pressure drop over the bit, which exceeds 500 to 700 bar. Then you get close to that limit and you may break down some of the particles. We stay at much lower pressure, and we have not seen edgy particles. Edgy particles you don't want to have in the circulation because they have sharp edges, and then you could damage some equipment. But we have not seen that in the operations anytime, anywhere. Yeah, so yeah, I hope this covers a number of the questions. Yeah, no, thank you very much.
What about the one question that I didn't hear covered in it is temperature, right? In geothermal, things can get pretty hot depending on what markets and geographic areas that you're looking at, or even depths. What are the upper limits to the temperature restrictions for using particle type drilling tech?
Yeah, no, the temperature restrictions are are determined by the electronics that is being used. So the control electronics, and of course also the directional electronics that are being used, the magnetometers and accelerometers and the control units, they should stay, and the batteries, they should stay below say 180 degrees, the operating temperature. And if you go to a formation that is hotter than that, you will have to apply some cooling mechanism during the operation. So if you have temperatures of the electronics that exceed the 180 degrees or 200 degrees, that range, then you are breaking down all these electronic components, and you're really cooked. So that's cooking while drilling and not cooling while drilling. So you have to choose between the two. And to get the cooling, of course, you can use insulated drill pipe and continuous circulation. There are also some cryo techniques that you could apply during, for instance, a circulation break for a joint, so that you can have at least temporarily a solution to keep the electronics cool. But yeah, we have not gone to these extreme temperatures because we are targeting first the shallow and deep. But of course, we are looking at the big drilling challenge for the ultra deep as well, and there we have to tackle these.
So you're referring more to the electronics in the platforms that you're integrating into, rather than the limitations of your Canopus bit itself, correct?
Yeah, that's correct. So the PDC bit has no temperature range, limit in the range of ultra deep even, and of course you need to change seals here and there, and you have to and the steel shot particles themselves are not affected by the temperature. So it is really the electronics that is that you have to resolve to be able to apply it at these higher temperatures, reservoir temperatures.
Okay. So changing gears a little bit and talking more about the comparative nature between particle drilling and what's used today. A question came that it was asking about the technology that was used at the Forge, which is the U.S. Department of Energy enhanced geothermal site in Utah. And the question came in asking, what's the difference between the particle bit drilling technology that was tested there at the Forge versus what Canopus is developing right now? If you know.
No, I don't know the details of the Forge project. What I do know is that the directional control that we have, and also the combination of PDC cutting and the erosive jet action, we had no problem patenting these. So I think that gives us a pretty good differentiating position. And once again, also I don't know what the details, like the particle diameter that has been used. I mentioned already that we have landed on a particle diameter for the steel shot that is 1 millimeter or a little bit less, and it is very important to restrict yourself to that diameter, because if you go to 2 millimeters, it's only a factor 2 bigger, but it's in 3 dimensions, and the hole cleaning and the circulation and the solids handling, it gets much more difficult if you go to larger particle sizes. I don't know whether that is so. I cannot judge the Forge project because I don't know the details. But I guess that these are the biggest differences.
Okay, so we are coming up at the end of our time. We have questions or time for one last question here. So what I'll ask here is, what haven't I asked you that you think I should have, or do you think that the audience should be asking you about your technology or your demonstrations?
I think the one thing that has not been addressed is whether there could be wear in the system or in the surface system because of the particle circulation. One of the golden rules that we have landed on is that we always everywhere should keep the velocity of the particles less than or 10 meters per second max, and preferably less. If you have steel material tubulars which are ductile, then if you stick to that rule of staying below the 10 meters per second, then you don't damage it, and that is what we have done, of course, during the pilot as well. So if you have bends at surface, of course, we checked them during the pilot as well, whether we had these challenges. We did an open circulation test at surface to ensure that there were no unexpected restrictions. And when you do such a test upfront, then you avoid these type of things the particles to erode in places that you don't want to. Then there could be another question which is in the similar range, and that is if you would have a well control issue with these particles, could you block a choke or whatever? Now, first of all, it depends on the flow rate whether these particles can reach the surface. If you don't have the hole cleaning criteria, then you will not pump them out. They will drop, but you will still be able to circulate through them. And because we use a relatively low concentration, you have to do the calculation, of course, but you will be able to get to circulate through the open structure of the particles because they are spherical. If you have solids in combination with the particles, you have to look at whether the mud properties that you have, etc., can indeed don't cause these problems. So you have to do some homework and some preparation and perhaps some testing because you add particles to the well, and every driller doesn't want to put particles in the well because that's exactly what you want to get out of the well. So you have to give up that thought. But if you do that, in this case with the steel subparticles, you get a lot of benefits back, and it is indeed valid that you do the preparation for that aspect of the circulation. Other aspects, backscatter from the bit on the hole bottom, etc. Bits are designed to survive that, and once again, if you don't have the edgy particles, that's not an issue. So
very good, Mr. Jan Jette. Thank you kindly. Really appreciate the wealth of information from the presentation. We are at our time limit right now. And so I will say that coming up next, after a short break, is Erica Salmanvara from Q-Heat, and she will be presenting after about a 5-minute break. Thank you, everybody. Thank you, Jan Jette.
Thank you, Taylor. Great pleasure.